Z. Okay. But for now, we're going to start with linear free energy relationships. And it's quite an interesting course. It's a very different course to even organic work, even though there's mechanism in it. And it's very different to physical chemistry. It's not quite fitting in any world. But I'm just going to start by saying there's an emphasis on linear. I had a problem when I first ran this course many years ago, is that when I set the final assessment task, people were drawing curves, and I was devastated because I thought that people would know, at least from the name of the course, that you had to draw straight lines. And so the emphasis is on linear, and so please invest in a good ruler. And of course, the physical chemistry is coming through, where physical chemists always want a straight line. And so we're searching for linear relationships in a set of reactions, or sometimes two linear relationships in a set of reactions. So please use a ruler in all of this, or if you're using Excel, make sure it's a straight line fit to the points of data that you've got. Okay. Now, there's some idiosyncrasies that I have. And so I just right up front want you to be aware of them. So if you forget some of the idiosyncrasies, just please stop and say, what do you mean when you say something that's unfamiliar? So first of all, I don't use the natural log. So on the calculator in this course, please don't use natural log. So to check that your calculator works correctly, just make sure that you can work out the log of 10. Or if you're using Excel, check that you can work out the log of 10. And it's a log to base 10 of 10, and it should be 1. If you get the log of 10 as being 2.302, then you're using the wrong log. Please, in this course, we're using log to the base 10. It's standard in this type of chemistry to be using log to base 10. So please make sure that's what you use. Another thing is that a really important compound in this course, it's interesting that you would have a course that's based around a really important compound, but this is a really important compound, is benzoic acid. So I'm not going to call it benzene carboxylic acid, I'm going to call it benzoic acid. Benzoic acid is really a critical key point in this entire course. We're going to come back to it. A final point is the penultimate point is Marcus structures. So this is how Marcus structures is represented. And it's a shorthand because if you want to talk about many different substituents, you just draw it like that, saying it could be substituted anywhere on the benzene ring. So a Marcus structure says that you could have any substituent X placed anywhere at different positions. So some examples that are covered by this Marcus structure are these compounds here. So here is orthochlorobenzoic acid. Notice I'm calling it benzoic acid. So the Cl is, I maybe should say 2-chlorobenzoic acid, but what we're going to call it in this course is orthochlorobenzoic acid. And of course, that's covered by the Marcus structure. So yes, there's a group attached to the ring. There it is. Similarly, metamethoxybenzoic acid. Apologies, that word is wrong there. It's not meta, it's not M-chloride, it's M-methoxybenzoic acid is also fitted by this Marcus structure. And of course, the para substituent. And you'll notice that I'm not using the 2, 3, and 4 substituent. I'm using ortho, meta, and para. So there we have it. So I'm using log and base 10. I'm using Marcus structures to represent a whole range of structures. I'm calling things benzoic acid instead of telling you the exact substituent position, I'm using these old terms, ortho, meta, and para. So please, this is the way I'm going to operate in this course, but stop me if anything's confusing, and we can always just reinforce what we need to know. Okay. Now, please don't look ahead in the slides. The question I've got, and of course we're working with linear graphs. The question that we have when we look at linear graphs is, does a straight line imply a causative link? Which means if you were to make a change, for instance, on the x-axis, so if you were to change its value, would it cause a change in y? Is there a link between the x that you've got here and a y over here? And just think about it for a moment. Well, in this case, is there a link? The data I've plotted, is there a link between it? You can see that the numbers, and not only is it a straight line, not only is it fit, the best line really, really fitting extremely well, but even the actual values of the numbers are matching. So at about 500, we've got about the same number. At about 3,000, we've got about the same number. So the question is, does a straight line imply that x causes y? And maybe it's easier to, well, like this, it might seem to be the case, but if you have a look at the next slide, what have I actually plotted? Well, I went to Google Analytics and I've searched for how many times people have searched during the year for headache cures. And I've got those values, and these are cumulative between January and April this year. And I also went on to have a look at, it's common knowledge how often Trump has been tweeting this year, and I've plotted against the two. So the question, maybe I'm onto something, maybe every time there's a tweet that comes out, people are suffering, and so they have to suffer, they have to search for a headache cure. Or maybe, or maybe these are independent. Maybe as a population, people will always come across, they will always have headaches, and maybe he is tweeting regardless of what's happening around. So just because we've got a linear relationship here, it might be nice to think that there's a causative link between these two, but actually there isn't. Maybe there's something else that both depend on, and that these are two unrelated systems. When we come to linear free energy, it's like that. We plot two unrelated things against each other, and yet we still get a straight line. And it is useful to us, and you'll see how it's useful to us in linear free energy relations, but it's always important to remember that just because you're getting a straight line, it doesn't mean that what's happening on your x-axis is causing what's happening on your y-axis. So please be careful of that. Linear does not mean causative, and this is true of linear free energy relationships. So if you go back to this graph, does it make sense to calculate an experimental error in the slope here? No, it doesn't. There's no error in the slope. You should not be plotting these against each other. So it's really great that we get a straight line. And when we work with linear free energy relationships, please never calculate an experimental error. We are just lucky that we get straight lines, and the straight lines have good meaning to us, and the value of the slope has meaning, but there's no sense in the experimental error. There's no sense in expecting there to be an error from the scatter. Are there questions? Okay. Right. Now, I hope that in organic chemistry, you've been on the search for trends. And I hope that you are aware of trends like, for instance, whether a system is going to undergo SN2 or SN1 substitution. And of course, we have the trend. If you've got a tertiary halide, for instance, it's going to be more likely to undergo SN1. It's more likely to form a stable tertiary carbocation, for instance. But of course, that will reduce as you go towards the left, as you go from secondary, tertiary, from tertiary, secondary, primary, so on. So there is a trend as you go. And I've drawn this as a curve here. because it's not a quantitative trend, it's a qualitative trend. We know that when we look at systems, we can try and decide whether it's going to undergo SM1 or SM2, and it's easier at the extremes to make that kind of a decision. But we here in this course, we want to try and see if we can't get a quantitative relationship between systems. So just to start off with, I'm going to consider two totally unrelated reactions. Well, they're not entirely unrelated because the R groups are going to match between the two reactions. So we'll have if we have the R group as, for instance, a methyl group for this reaction, we'll have a methyl group for this reaction, and we will compare the two. Now, the first reaction is a base catalyzed hydrolysis of esters, and this has a rate constant K. The second one is the acid dissociation. So you'll see that you're going from a carboxylic acid to the carboxylate and H3O+. And of course, you have an equilibrium constant for that. So I'm not only comparing two different reactions, I'm comparing two different values, a rate constant and an equilibrium constant between these two reactions. And maybe you're not going to be too surprised when you see that when I compare these two reactions, on the y-axis, I've got hydrolysis of esters, the rate of it, and on the x-axis, I've got the acidity constant, that there does not appear to be any relation at all between these two reactions. So you can see that I've taken the log of the equilibrium constant for this reaction, and I've plotted against the log of a rate for that reaction. And the only thing that's in common between these two really is the R group. So over here, on this graph, I've only shown the ester part of it. So this dot here at 2 is showing the rate for the hydrolysis of that ester of the chloroethyl ester of benzoic the ethyl ester of chlorobenzoic acid. But of course, what we're plotting it against on this axis is, of course, the acidity, the dissociation constant for chlorobenzoic acid itself. So we're comparing these, we're comparing an equilibrium constant against a rate constant. And we notice that we've got no comparison between the two. But it might be interesting to think why we've got no comparison between the two. And this dissociation constant is possibly the nicest one to look at, because the only thing that's happening in here is the exchange of a proton. A proton is tiny, and so this exchange will happen quite readily. It'll go back and forth quite readily, and there'll be no interference at any point between the proton. But it maybe is more interesting to have a look at the hydrolysis of the esters. What is going on with the hydrolysis of the esters? Maybe complications are taking place in there that maybe lead us to have a greater scatter on a graph like this. So let's have a look at the mechanism for hydrolysis of an ester. Right. So hydrolysis of an ester. So I've just chosen a substituent for the hydrolysis of the ester to be an aromatic system. We're going to be using aromatic systems quite a lot. And you'll notice that I'm using the Markov structure, which means that as you change R, you're changing an R group could be at any point on the benzene ring. But the hydrolysis of an ester starts with attack of the carbonyl by an OH minus. Okay, it's then going to form a tetrahedral intermediate. So OH minus is going to come in, and now we've got carbon with 4 bonds attached. It's a tetrahedral carbon. Right, and then of course we lose the carbonyl reforms, and we lose OH minus. I hope you can see the minus there as a leaving group. And of course the equilibrium means that we will, the proton will very readily exchange between the carboxylic acid and the OH minus to form ethanol at the end, and we'll have the carboxylate at the end. Now, as you look at this, the loss of a leaving group is not going to be so difficult. The slow point is going to be forming this tetrahedral intermediate. That's going to be the problem in this entire reaction. The rate of this reaction, which is what we're looking at, is going to be dominated by the rate determining step, which is the formation of this tetrahedral intermediate. So the question is, what will complicate the formation of this tetrahedral intermediate? And really, it boils down to steric bulk. As you get the OH minus coming in, question is, you can see in the tetrahedral intermediate, you're going to have to fit a lot more around your carbon atom. And so the rate might be dominated by things that fit around that carbon atom. And so I've tried to spell it out for you. So I've got some different situations for these two reactions. So on the left, this is acid dissociation. And you'll notice for the R group, I've chosen an ethyl R group here. And over here, I've chosen a meta-substituted, an ortho-substituted chloride derivative over here of an aromatic system. And here's a para-substituted system. So you'll notice that for the acid dissociation, all you have to do is remove this proton here. See, it's gone. And so there's no steric interaction with this R group. There's no problems at all. So I've not drawn anything big here because there's no problems that are created during the course of reaction that interfere sterically with these, with the R group over here. Similarly over here, it doesn't matter that I've got the orthochloro substituent. It doesn't matter because we simply lose that proton and it forms the carboxylate immediately. There's no problems being formed. Even with a para-substituent, losing that proton is no problem at all. But what about ester hydrolysis? If you look very carefully at ester hydrolysis, you'll see that as the OH minus comes in this case, and this carbonyl oxygen becomes O minus, and that O minus is then going to bump with the ethyl group here. I've tried to draw it as showing the size of the atom, so it's easier to see how that O minus that gets formed going from sp2 to sp3 is now bumping with the R group that we have there. So the steric issue, there's a huge steric issue as you do ester hydrolysis of this system where you've got an aliphatic substituent there. What about the aromatic substituents? Well, if you've got an ortho-substituted system, the OH minus coming in is again going to make that O minus there. And as it comes in, that O minus is going to come into close proximity with that ortho-substituent. So there's a steric issue again over here. And compare it with forming the acid. There are no steric issues over here, but there are huge steric issues in the ester hydrolysis. So acid dissociation with movement of of a proton is easy, but ester hydrolysis is not so easy with formation of the O minus. However, in the para-substituted benzoate ester case, it doesn't matter that that O minus gets formed over here. And I'm not drawing it large because even if I drew it large, it's not going to interact with these hydrogens on the aromatic system. The para-substituent is far enough away that there are no steric issues at all with the para-substitute system. So there are problems with our comparison with our acid dissociation on the left and our ester hydrolysis on the right, is that you're trying to compare systems that have no problems sterically with systems that have problems sterically. In the only case really where a comparison would be nice is in the para-substituted case, where you've got no steric problems in the acid dissociation and you've got no steric problems in the ester hydrolysis. And that's interesting. If we go back to our horrible scatter plot and we cut out the ortho-substituted cases, cut them out, see they're now gray. If you cut out the aliphatic systems, what are you left with? If you leave yourselves with only meta and para-substituted systems, you'll find that you get a beautiful straight line. And it's interesting, we've managed to discover a straight line between two totally unrelated reactions, acid dissociation and ester hydrolysis. And we got the straight line by limiting ourselves to cases where no steric problems arise during reaction. So this is quite interesting. So when we search for a quantitative relationship, we need to compare only meta and para-substituted aromatic systems. So here's my Markish representation. We must just remember that in the Markish, we're not going to look at ortho-substituted. It's only meta and para-substituted systems that we want to look at. And then we are comparing the base catalyzed hydrolysis of esters and the rate of that with the acidity constant for the corresponding acids. So what we can do is maybe we had only 3 systems that were in a straight line. So let's try and extend it for more systems, and it's not too bad. And there's a lot of scatter, but you can see that I've now populated it with many different systems. So don't forget that, for instance, if you've got H here, then of course we're only looking at substituted aromatic systems. So this will be for H, it'll be benzoic acid, and it'll be the acidity constant for benzoic acid here. And if you take the log of that to base 10, you get about minus 4.2. And of course, the rate of hydrolysis of the ethyl benzoate ester with no substituents, only H's on the ring, then you will get a rate constant, and we get the log of that rate constant, and that's maybe at about minus 1.3. And so what we've got is we can plot that. We can plot it for all other substituents, and we get a straight line. So the question might be, why on earth do we call it a linear free energy relationship, and why do we get a straight line? Okay, so firstly of all, remember that if you take the log of a dissociation of a K, log of K is related to a free energy of change in reaction. And don't worry, also remember that if you take the log of a rate constant, that's related to the activation, free energy of activation in a reaction. So the logs, the log of the capital K and the log of little k, are related in some way to free energy changes or free energies of activation. So what we're plotting against each other are linear free energies. But the more difficult question to answer is, why do we get a straight line? And that's a tough one to deal with. But maybe we can, at this point, just think that maybe there are factors. Maybe there are factors from the groups we have chosen that affect one reaction in the same way. But further to that, that affect the free energy change in one reaction to the free energy in the same way that it changes the free energy of activation in another. And this will start to make more sense when we start to look at the groups that are attached to the aromatic system, and those groups that have electron donating and electron withdrawing properties. So maybe having an electron donating group somewhere on the ring is going to affect the free energy of change in the one reaction in a similar manner to the way it affects the free energy of activation in the other reaction. Okay, please don't worry about these 2 expressions. What I'm trying to say in these 2 expressions is that log of K is related to a free energy change for a reaction. That 2.303 that is over there is because I've used my log to base 10 and not the natural log that we normally use. And similarly, the log of rate constant is related to the free energy of activation. And of course, the 2.303 is because I'm using the log to base 10 instead of the other log. So the question I have is, does anyone have any questions, or would you like me to clarify some points that I've worked through now? Okay, so what I want you to be, the take home from this is that what we've got to do in this is that we can compare, and we are going to be comparing reactions, but we must have an aromatic ring attached to them, which means that we're going to be working with benzoic acid and substituted benzoic acids. And of course, what I'm showing here are the esters of those benzoic acids. So here's the ethyl benzoate. So there's the ethyl ester of benzoic acid. There's the paranitro version, and there's the paramethyl version. If we compare the dissociation of the acids, where you put H there, with the rate of hydrolysis, base catalyzed hydrolysis, we are able to get a straight line. Now, what's going to happen in future slides is that I'm going to keep this reaction the same. So I'm going to call this our reference reaction, or this is our standard. It's probably a more accurate way to describe it. That's our standard. And this is the reaction of interest that we want to study. So please remember that we're going to be working with COH, benzoic acids, all the way through in this reaction. Okay. If you have questions, please feel free to ask me. I just want to spend a few minutes just discussing a prac that is on Are You Connected? So what I have done, for those who have not yet done the Perl scripting prac, which might not be all of you, but you're welcome to look at this if you're interested. I just need to find, there we go. So if you go to calcium as before, we've been using in the molecular modeling, we've been using WebMo Pro. And we've got WebMo Pro until about the end of June. So please don't, if you have not done the modeling prac, please try as soon as you can to do it. I'm trying to extend, I'm trying to change our local WebMo standard to WebMo Pro, in which case we'll be able to carry this on beyond June. But I would like you to try as much as you possibly can to get the modeling done before the end of June. But of course, the alternative to the Perl scripting prac, you're going to be using Jupyter. That's also on calcium. So when you go to Jupyter, you'll log in much the same way. I'm using a different login. I don't have a student number, so I'm just going to log in, but you'll be able to sign in using the same passwords that we have done before. And the first thing you do when you come up to this is go to this part in the end that says new, and you'll be able to create a new notebook to work with. And when you've got a new notebook, you'll be able to start running through the exercises that precede the prac. So there's a whole set of slides that are placed as exercises for the prac where you can simply type in. So I think the first thing that you have to type in, you have to type in a sum, which I think is to calculate the molecular mass of water. And so I'm going to type it in. So that's the mass of hydrogen plus 16.00 for oxygen plus 1.008 for hydrogen. You can space them as you like. And then the first thing you do once you've done that is you type run, and then you are able to get an output for that. But please have a look on Are You Connected? I'm going to show you on Are You Connected that you, I've got this here is right at the bottom of Are You Connected? And this takes you through step-by-step logging in and all the steps that you have to do. Follow this through, and that will be the first part of the notebook that you have, and then do the task that's in the other document, and then the two of them together will be the replacement for the Perl scripting prac. This is quite an interesting task that I'm setting in this. We're going to be looking at a particular molecule that has activity against a certain enzyme for COVID-19, and we're going to see if we can make it have better human properties for oral absorption to be able to work as a drug. So it's a really interesting prac. So even if you're interested, you're welcome to try it, even if you've already done the Perl scripting prac. And of course, as always, if you've got questions at any part, feel free to drop me an email, or if there's a small group of you, I can even start up another Zoom session to help with describing any aspect of the course or the pracs. Any questions? Okay, well, if you have no questions, I look forward to hearing from you and for your submissions for the various tasks. I'm going to be carrying on with the marking that I'm doing, so look out for that, and feel free to contact me if there's anything that you need clarity on.